In the stoichiometry section, we can investigate the quantitative significance of a balanced chemical reaction. And what this is going to allow us to do is determine the number of grams that need to react, and it can also give us the number of grams of a product that is produced in a chemical reaction. So the example that we're going to look at is CO, carbon monoxide, plus hydrogen gas, giving CH3OH. So first, we need to balance this particular reaction, and in order to do so, we need a coefficient of 2 in front of the hydrogen. So we have CO plus 2H2 giving CH3OH. And notice that for every 1 mole of CO and 2 moles of H2, we get 1 mole of our product, which is CH3OH. And what we can say about this is that stoichiometric factors relate the molar amounts of any two substances in a chemical reaction. So the balanced chemical equation gives us the ratio of all the moles of every component that's involved. So here we have a 1 to 2 to 1 mole ratio of everything, of all the reactants and the products in this particular equation. So from this we can answer various examples, like the following. So in this example, we're going to ask how many moles of H2 is needed to produce 5.4 moles of CH3OH. So initially, we're going to start with our 5.4 moles of CH3OH. That's our given unit. We're going to use dimensional analysis to figure out how many moles of hydrogen are needed to produce this. So if we have 5.4 moles of CH3OH, we now need to go back up and look at the coefficients in the balanced chemical equation. And like we said, stoichiometric factors relate the molar amounts of any two substances in a chemical reaction. So for every 1 mole of CH3OH that are produced, we are going to need to consume 2 moles of H2. So the moles of CH3OH cancel, and this is going to give us 10.8 moles of H2. And this conversion right here comes from the balanced chemical reaction. And this is why we spent a decent amount of time balancing chemical reactions, because the balanced chemical reaction is going to allow us to determine which or how much of a particular product is produced and how much of that reactant we need to produce the amount of the product. So if we kind of provide a template for all the calculations we can do with stoichiometry, we know that in general, in a reaction, we can take moles of component A and interconvert to moles of component of species B. These can either be reactants or products. And the balanced chemical reaction is going to allow us to do this, just like we did in that previous example. We can also convert moles of species B to grams of B. And we can do this by using the molecular weight. We can convert from grams to moles and from moles to grams. Now, we can also go over here to species A and convert moles of A to grams of A. And we can convert grams of A to moles of A. And again, we use the molecular weight in order to do this. Unfortunately, there's no direct step to convert grams of A to grams of B or vice versa. So if we're given grams of component A, and we're trying to get grams of B, we can't do it in one step. We first need to use dimensional analysis to convert from grams of A to moles of A by using the molecular weight, convert moles of A to moles of B from the balanced chemical equation, and moles of B to grams of B using the molecular weight. So we can do a quick example using the following balanced chemical equation. We have 4NH3 plus 5O2 giving 4NO plus 6H2O. What we need to determine here is how many grams of H2O would be formed from the complete reaction of 5.0 grams of NH3. So here we're going to take grams of NH3, convert to moles of NH3, moles of NH3 to moles of H2O, then moles of H2O to grams of H2O. So we'll start with our given quantity, which is 5.0 grams of NH3. There are 17.0 grams of NH3 in 1 mole of NH3. And we can do that by using molecular weights from the periodic table. Now we need to convert moles of NH3 to moles of H2O. We use the coefficients in the balanced chemical equation. There are 4 moles of NH3 for every 6 moles of H2O. So 4 moles of NH3 go in the denominator, and 6 moles of H2O will go in the numerator. The last step is to convert the moles of water to grams of water. So for every 1 mole of H2O, we can add up everything from the periodic table to get 18.0 grams of H2O. This will give us 7.9 grams of H2O. So when we look at what we're doing, this is our given quantity, which is 5.0 grams of ammonia. We then can use the molecular weight of A from our chart up here to convert from grams of ammonia to moles of ammonia. Then, from the balanced chemical reaction, we can convert from moles of ammonia to moles of water. Finally, we use the molecular weight of B to convert moles of water to grams of water. This gives us how many grams of water are produced when 5.0 grams of ammonia reacts.